Okay, so we have few people missing, so we'll wait for them, maybe another minute or so, and then we'll go ahead and start. All right, so I guess we can go ahead and start. So I'm gonna go over chapter 7 today. And should be plenty of time for me to finish chapter. And on Wednesday, we're gonna cover chapter 8. So technically the two chapters we're gonna cover this week, week 4, will be chapters 7 and 8. All right. And don't forget, so tomorrow you should be going to campus to have the lab and campus. So I'll have someone subbing for me. All right. Okay, so I'm gonna go ahead and then basically have everything here. So we have chapter 7. All right, so I imagine most of you already have used Zoom before. So if you guys have any questions, so Zoom has the option of raising hand. So let me see, they did make some changes. But let me see where that option is. All right, so here you go. So this option over here, if you do the raise hand, then that will basically let me know that somebody has a question, and then I can stop and give you a chance to ask me a question. But please go ahead and use this every time you have a question during the lecture. And I think once you have your question answered, you're gonna have to go back and lower your hand. It doesn't do it automatically. So, all right, so raise your hand and lower your hand. This is the at the bottom you will see it says react. So if you press that, it does show you lower hand and raise hand. So go ahead and use that again during the lecture if you have questions. All right, so let's go back here. So chapter 7 is still, we are looking at the Newton's laws of motion. So this is an application of Newton's third law. It's mostly, we have more than two objects interacting. There's interacting objects. So one of the things we will see here is, for example, you have, let's say you have a box of mass M. So if you are pulling this to the right with some tension force, okay, so this is pretty much tension is equals to mass times acceleration. This is just a simple application of the second law. But the difference here is what we're going to do here is like, let's say, what if there's another one right here? So this one becomes an M1, this becomes an M2. And then mass 1 and mass 2 are connected together by a rope like this. So let's say there is this rope 1 right here that's going to be basically connected to mass M1, and then rope 2 connecting M1 and M2 together. Now what we're going to do, we're going to pull it with some 20 newtons of force on rope 1, basically, pulling that mass 1. And then what we have here is then, because mass 1 and mass 2 are connected, then both of them now are going to move together. Okay. So what we have here is then this equation more or less going to be similar to what we had for one object. The difference here is going to be then this tension now acting on the system of two mass object. That means it's going to be then M1 plus M2 times acceleration of the system. But now we have two objects. So that means you have object 1 has acceleration 1, object 2 has acceleration 2. And the question is that how are those two related? Well, the way they're related here is if you pushing this tension 1, we can call that tension 1 because, so this is a rope 1. So rope 1 then going to give us tension 1. So tension 1 is acting on mass 1 directly. It's not acting on mass 2, but M1 and M2 connected by rope 2 where there's a tension 2. Because of that connection, you're going to have same acceleration actually applied to mass 2. So acceleration of object 1 is always going to be the same as acceleration of object 2 if they are connected. That means any 2 connected or 3 connected or 5 connected object, as long as they're connected by some way, they're going to always have the same acceleration. So that means we can always say that there's acceleration of the system A, assuming that we understand that they're all going to have the same acceleration. So rope 1 only acting on mass 1, but because mass 1 and 2 connected by rope 2, both will accelerate together with the same rate. But the tension here, if you look at the acceleration, tension here will be then, let's say 20 newtons, then divided by the total mass. And let's say both of them are 5 kilograms, then it's going to be 10 kilograms. So you get 2 meters per second square. 2 meters per second square acceleration. Where before, if it was just that 20 newton acting on 5 kilogram, it would have then, much higher acceleration before, which would have been 4. The idea here is that you can always assume that this is going to be then external force. So external force is some kind of external force acting on the system. But then here, tension 2 is the tension in the rope that connects those M1 and M2 together. So that is actually going to be known as an internal force. And you can see, right, in this equation, this is just only external force gives you acceleration of the system. So if you're using this equation, it ends up being tension 1 equals total mass times acceleration of the system. You guys have any questions? Now, for example, let's say you want to know how to find tension 2. Well, if you think that tension 1 and tension 2 are the same, they're not. So if tension 1 is 20 newtons to the right, tension 2 is going to be different because it's coming from a different rope. So at this point, the way we would find information about tension 2 is if you look at the system. This is object 2. This is object 1. And this is then rope connecting those two. And then this is the second rope connected to M1. So here we have tension 1. And then here we have tension 2. And let's say there's no friction. If I want to find then tension 2, what I have to do here is I have to then create a smaller system. That means break down my entire system into 2 smaller systems. So this will be then system 1, and this will be system 2. Because if I look at the whole thing, you can see, right, if I'm looking at the whole thing, this internal tension information kind of goes away. It's you know, this is just an external force equals total mass times acceleration. But if I want to know internal force, I have to break it down into 2 smaller systems. And then, for example, at this point, I can look at either system 1 or system 2 to find the tension. Because, for example, if I look at this system 2, which is a little bit easier actually, what I have here is the system 2. If I do free body diagram for system 2, let's say here's the object at the center. What I have for system 2 here is only one rope acting on it, which is rope 2, and it pushes it to the right. So tension 2 comes from rope 2, and there's, you know, normal force. So normal force 2 because it's box 2, and then we can put like a gravitational force 2. So what I have here is, if I'm looking at forces, so I have tension 2, I have FG2, and I have normal force 2. So I can then see that I have horizontal and vertical. So the best way is to look at the table. So tension 2 is to the right, positive. It has no y component. Gravity is negative, so it's M2G in the negative y direction. Normal force has no x component. It's in a positive y direction. And those two are going to cancel out. But tension 2 is the only horizontal force. So what we're going to get mass times acceleration. So mass 2 times acceleration 2. So here, then I can say that equation 1 for this system 2 will be horizontal net force tension 2 is equals to mass 2 times acceleration 2. And in a y direction will be normal force equals M2G. They cancel each other. And you can see, right? Let's say we said that both are 5 kilograms. And then when we calculate acceleration from external force, we got 2 meters per second square. And I can just go ahead and solve for that. You can see, right, it's going to be 5 kilograms times 2 meters per second square. And what we got here is 10 newtons, which means the tension 2 that connects those two is 10 newtons, where the tension 1 that was connected to mass 1 and is external force pulling the whole system was 20 newtons. So this is how we can then get information about that internal force. So we had to like break it down into like 2 parts, right? Or, basically look at individual box, and then we can get it from there. We could have also looked at system 1. So if I look at system 1, it would have been box 1 with 2 forces acting on it. So it would have been tension 1 to the right and tension 2 to the left. And then let's say right now, just looking at the horizontal, ignoring the vertical, it would have been then T1 minus T2, because T1 is to the right positive, T2 to the left negative, would have been equals then M1 times acceleration. So you can see, right, if I rearrange and so for T2, it would have been then T1 minus M1 times A1. And from here, I could then just calculate T1. We calculated that was given to us 20 newtons. Mass 1 was 5 kilogram. Acceleration was 2 meters per second square. 20 times 20 minus 10, we could see again, we're going to get 10 newtons. Exactly same as we got over here. So either way, we could have just, either system 1 or system 2, we could have solved for and get tension 2. But from this particular example, we can see that the rope that connects tension, box 1 and box 2 is, again, it's inside the system, so it's an internal force, but it's the same 10 newtons that is acting on M1 and M2. That means if you look at over here, right? If I'm looking at M1, which is right here, then the rope acting on M1, this rope 2, acting on M1 to the left. If I'm looking at M2, this same rope acting on M2 to the right. So that's why it's an action reaction, right? It's a Newton third law application. And what I have here is same 10 newtons acting on both of them, right? So that's why we had to kind of separate them. We have to look at either M1 or M2 in order to get information about this tension too. All right, any questions? All right, so more or less, this is how we're going to solve problems dealing with this Newton's third law application in this chapter. So if you're okay with this, then more or less the rest of the stuff here is just solving different type of problems and getting, let's say, more comfortable with dealing with, you know, something like this. So one of the ways that our textbook kind of, you know, deals with this here is to consider the type of, let's say, this type of force, right, as in terms of interacting diagrams. So interacting diagrams, I don't necessarily use it. Our, you know, textbook kind of goes over it, and I go over it in the video lectures and things like that. So interacting here is in terms of, let's say what objects interact with one another. So, for example, I mentioned that before. Let's say here a person is walking. And what we have here is, if you remember, right, I told you that when you are walking, what you're doing, you're pushing the ground backwards. So this is the force that person exerts on ground. And then what ground does, it pushes on the person. So this is the force that ground exerts on the person. And then what we have here is that these two forces are what we call interacting forces. Because if I take then ground, that means I can take, like, let's say here's ground and here's person. So there are two things that are interacting with one another. And these two forces then are basically example of action reaction. So the action of person pushing the ground has equal but opposite reaction of the ground pushing back on the person. And those forces always going to be the same magnitude, but they're going to be in opposite direction. Same thing you can think of it here is if you have a box on the ground, and let's say this box is being pushed. Let's say there's a force acting on it to the right. Okay. So, and let's say this surface here is rough. So there's a friction. So one of the things we can think of here is, so let's say there's a force acting on it from the ground. Let's say this object here is moving to the right. So direction of motion. So motion is to the right. Then what I know here is then the friction going to be acting always opposite of the motion. So here's going to be the friction. So this is the friction coming from the, so this is the friction, right? From the ground on a box. Okay. So this is the friction on the ground from the box. Okay. So this is, you know, something we've seen before. Now, one interesting thing we can do with this type of problems is what if, let me change this a little bit. I'm going to say that this is surface on the box. Okay. Because its surface is more, let's say, general, right? It doesn't have to be ground. It could have been any type of surface. And for example, we can also have something like this. Maybe it's not, you know, the surface is part of another box, a bigger box. Then this will be then, you know, M1, this will be then M2. And maybe they both, you know, are moving or something like that. So then what we can think of here is this, right? So right now there's a surface, and this particular surface, this part of the surface, right, is point of contact between those two boxes, M1 and M2. For example, I could also have this, right? So there's a normal force acting on M1. But now this normal force is coming from, surface of M2, the box 2. So that means I can say here's normal force 1 acting on, box 1. Or I can say this is normal force. Let's say here I can now again change the subscript a little bit. I can say this is then force that box 2 exerts on box 1. Okay, and this will be then the normal force of box 2 on box 1 because of that surface. Now what we have here is then if I take both of them part of my system, then I also have to look at the interaction of M1 on M2. And what happens here is, if I'm looking at that, exact same thing that is exerted on M1 from M2 will be on M2 from M1. So for example, there's going to be a normal force that 1 exerts on 2, which is exactly in opposite direction, but with with the same strength. That means, for example, N21 is equals to N12, but this one is going to be negative because it's going to be acting in opposite direction. Same way, there's going to be a surface friction coming from 1 on 2, like that. Okay, so those are, then we can think of here are what we call interacting. So interacting forces means these are 2 are interacting forces, and those 2 are interacting forces. Because those are 2 interacting objects, M1 and M2, and normal force and friction is due to the fact that they are physically in contact with one another. Okay, any questions? Right. So this is the difference that we're going to be dealing with in this chapter. So this also, for example, can be between, let's say, 2 boxes that are sitting like this. So here's M1, and let's say here's M2. Same idea, right? Same idea. Let's say at this point, so M1 exerts normal force on M2, and M2 exerts normal force on M1, something like that. So this is going to be basically the case. So the idea is this is due to the fact that they are physically in contact right here. Okay. Now, a lot of times what you're going to see here is something like this. So let's say there's no friction. Let's say you have those 2 particles are sitting there, there's no friction. And let's say somebody is pushing M1 with some force. Means like, let's say there's a force acting on M1 due to this person. Next we're going to say, okay, here's the force. So, or think like this, right? So I'll just do it like this. So there's a force like this acting on M1. Let's say it's 20 newtons. Well, what happens here is this 20 Newton force acting on M1. So it's not acting on M2, but because those 2 are connected, any force acting on M1 going to have the effect on M2. Because if you push with the 20 newtons on M1, both of them are actually going to move. They're both of them going to accelerate, assuming there's no friction, right? So this is going to accelerate the system. Okay. Well, the difference here is that this 20 Newton is only acting on M1. So if you want to know how much force actually is exerted on M2 to make it accelerate, is not going to be this guy. What actually accelerates M2 is the normal force that 1 exerts on 2 that acting on the box M2. All right. So this is actually, and this is going to be always, in this case, right, less than this applied force. Okay. So those are the, interesting things about this type of problems. That means if I want to know what is the normal force between them, again, I have to like separate, M1 from M2 and just look at individual systems in order for me to find that. Okay, so we have a few examples we're going to be able to see. And hopefully, you guys, 3 examples, will get a little more comfortable with this. But again, let me know if you guys have questions. Here, we start with something like this, kind of similar to what I just did. All right, so imagine you have two blocks, block A and block B. And what we have here, there's a hand in the figure that is pushing on block A, on the back of block A. And block A and B, we're going to take this M of B, mass of B, which we can see from the picture as well, right? The block B is a little bit bigger, so we can assume it has a bigger mass. So M of B is greater than M of A. And if you want, we can even put some numbers, right? So we can say, let's take M of B to be 5 kilograms and A to be, let's say, 3 kilograms, which kind of satisfied that. All right, so, and what we have here is the question says, okay, so they're connected by massless strings. And this is another thing that is important. So if we take the strings to be massless, then it allows me to say that tension is the same everywhere. So tension, same everywhere. Everywhere, I mean everywhere on the rope. That means, for example, any part of the rope that I look at, the tension is exactly the same. If, let's say, rope or a string, doesn't matter. But if the string in this case is not massless, I would not be able to make this assumption, because in that case it will have, different tension here, different tension there, and it will have a like acceleration. But it's not something, let's say, I'm interested in, and we can actually easily make that assumption, because, for example, if I take this one to be 5 kilogram, this one to be 3 kilogram, maybe the string here is, I don't know, let's say 100 gram or like 50 grams, right? It's a big difference. Let's say if string is 50 gram, then block B is 100 times heavier, right? 5 kilograms, which is basically 100 times heavier. So we can kind of completely ignore that. So massless string means that, let's say whatever tension I have here, I can just say tension in the entire string. And I can, again, ignore different parts of the string. One thing to keep in mind is that if I look at B, this rope or the string exerts force in this direction. But if I look at A, the string exerts force in opposite direction, because, remember the force or tension from the string always acting in the direction of the string. So for B, the direction of the string is to the right, or A, direction of the string is to the left. So we have to kind of take that into account. All right, so I guess the question is this, right? Taking surface to be frictionless, we want to know, is the force of the string on B larger than, smaller than, or equal to the force of the hand on A? So basically what we have here is something like this, right? So there's going to be a force acting on A, let's say force from hand, let's put it like that. And then if I'm looking at B has then a tension force acting on it to the right. Okay. So let's say this will be force of hand acting on A, or tension from the string acting on B. I guess the question here is this, right? So how are those compared? So is this greater? Is this one, smaller, right? Are they equal to one another? And things like that. All right, so let's see what we can have. Again, one of the things we can do here is to probably see this better. Let's have some numbers. Okay, let's say let's assume that this is, for example, 30 newtons. Again, just some kind of made up number. So 30 newtons. And 5 kilogram, 3 kilogram, and you have a 30 newtons. Now the idea is, you can write this hand that exerts 30 newtons of force only pushes A, not B. That means this force is not acting on B, it's only acting on A. So for example, if there was no string, that means A and B were just independent from one another, just sitting on the surface, then we can just ignore B altogether and just look at, okay, so what happens on this 30 newtons acting on A? If A is 3 kilograms, then the acceleration would have been 10 meters per second square, right? Force over mass. Would have been extremely easy stuff. But what I have here is, there's a string connecting A and B. So this 30 newtons of force acting on A pushes A, but because A is, connected to B, so indirectly it's also dragging block B together. So again, remember, right? So if it was just this, then this 30 newtons divided by 3 kilograms would have given me 10 meter per second square acceleration. Acceleration acting on A. It would have been just, that's it. But because of now B connected to A, it has to now also push B indirectly. But amount of force acting on B, which is this tension, right? That's what we want to know. Are they the same or are they different? Well, one of the things we can do here is this, right? So identify which one is an external force, which one is an internal force. All right, so let me ask you this. What do you guys think? Which one of them is the external force? Who can help me here? Which one of them here is the external force? Are you guys there? Anybody? All right, so let me see. All right, guys, okay, so you don't have to, let's say, send a direct message. You can just do a message to everyone so everybody else can see. Yeah, you can either put it in the chat room or just speak up. So I have an answer, hand pushing A. Yeah, that means at this point, FH is external force. So external force, which means that I can think of, like, let's say, since A and B are connected, I can think of this as a system like this. And external force F of H is acting on it, which means that I can say that F of H is equals to total mass times acceleration of the system. And in this case, I can calculate then acceleration of the system as external force Fh divided by total mass. So this will be then 30 newtons divided by 8 kilograms. And let's see. I get 3.75 meter per second square. You can see, right, I already went quite much lower acceleration by including B in the system. So 3.75 meter per second square acceleration. Now, the important thing to remember about this type of problems is that now that I have two systems, two things connected to one another, so A and B connected to one another, because they are connected, they're interacting, they're going to have exactly the same acceleration. So they can have exactly, in this case, A of A and A of B. They're going to be exactly the same. They're going to be the same as the system acceleration. That means I can say that acceleration of A, same as acceleration of B, same as my system acceleration. So it's going to be 3.75 meters per second square. They both have exactly the same acceleration. It just happened to be that because they are connected and there's external force acting on the system. Now, what I can do here is, now that I know that, to find information about internal force like tension again, like I said, right? So I have to then take this and break it into smaller parts. So just look at B. And if I look at just B, because there is no friction, the only horizontal force acting on B is then the tension to the right. So then from here, I can calculate tension acting on MB times AB, which is MB times A, because it's a system acceleration. And I can solve this because 5 kilogram mass has the same acceleration as system, so 3.75 meter per second square acceleration. Then I can say that the tension as a force is 18, let's say roughly 19 units, 19 newtons. Okay, so 19 newtons, which means it is much less than applied force of the hand. So that's kind of what we have, right? Because you can think of it like this from the conceptual point of view, that force from the hand has to push both A directly and B indirectly. So it pushes two blocks together, where tension is only responsible for pushing block B. Okay, so that's why force of hand is much higher and tension in rope on the string is lower. You can think of like, let's say if I have some kind of additional mass here, MC, and then there's another rope connecting those two, then I would make this as tension 1, and here's tension 2. Because every time you have a new rope, there's a different tension. So here's my question then to you guys. If this is this case, how would you then compare tension 1 and tension 2? What would you do? Do you think this tension 2 would also be 19 newtons, or will it be different, and why? Again, you can speak up, or you can just type it in the chat room. Okay, so I have one student saying same, then someone else says different. But how different? Remember, my question is, how are those two connected? How will they be connected? So let's not kind of like compare it. So you have T1 and T2, right? In this case, here's string 1. There's a tension 1, and here's string 2. There's a tension 2. So what can you say about that? So okay, a couple of students saying they will be the same. Well, let me say that they're not going to be the same. They can't be the same, right? With the same logic as FH and T1 are not the same. See, F of H pulls 2 blocks, T1 pulls only 1 block. In this case, it will be in this case, F of H will be pulling 3 blocks, T1 will be pulling 2 blocks, and T2 just only going to be pulling 1 block. So that means T1 will be greater than T2, because T2 only is responsible for pulling just 1 block. T2 only pulls MC, and T1 pulls, both mass of C and mass of B together. So that means more blocks you are kind of pulling to the right, stronger the force should be. So that means at this point, we can more or less say this T2 is less than T1, which is then less than F of H, as we already saw before. So that means if I have more and more and more like this, right, every time the tension will be, less. So if I have like another A, B, C, D, and then this is T3, and T3 will be even less than T2, and so on and so forth. Means closer you are to the last block, weaker the strength. further away, more blocks you're pulling, stronger it generally is. All right. Let me know if you guys have questions on this, but more or less, this is like a conceptual question, but it's just easier to see from the point of view of putting some numbers and things like that. And you can see, right, in this case, hand had a stronger force than tension. All right, so here's another one. This one a little more complicated because it has more we have two blocks. It's an incline and there's a pulley and so on and so forth. So we're going to be seeing plenty of problems like this in this chapter. All right, so you have two blocks, A and B, and we are told that A is heavier than B and is sliding down. Okay. All surfaces have friction. And here's the interesting, right? So it says all surfaces have friction. So before we would have only like one surface, right? It would have been like, okay, here's a surface. But here, all surfaces have friction means that you also have A and A, B sitting on top of A, and the surface between them also counts. So you have to take that into account, and which means that is also a part of the system that we have to consider. And at this point, we have to look at it in terms of that is something that we have to consider as a surface with a friction. Okay, so that means we have now two surfaces. So this is surface one, and this, let me use a different color. So this is surface two. Surface one and surface two. We do have just one rope. Even if this rope goes over the pulley and comes back, this is just one rope. This is still just one rope. And one of the things we can say here is if it's a massless rope, and we are given that, right? The rope is massless. That means we can say that tension is exactly the same. And what we have here is this. The rope exerts force, you can say, right? It exerts force in this direction on B, so this is TB, and it also exerts force on A, this is TA. So at this point, remember the force of the tension always in the direction of the rope, right? But here we can just say that TA is equals to TB. That means the same tension force, same strength acting on both A and B because it's exactly same rope. Okay. But you have to look at it in terms of like there's a force TB, there's a force TA acting on individual blocks. They just happen to be exactly the same strength. So in a way, at some point, we can just say this is just T because it's exactly the same tension. All right, so there's also says it's a massless pulley turns on a frictionless bearing. Now, this is also important because we're gonna have a pulley here, okay, that in a way, because it's massless and frictionless, doesn't really affect the motion in any way. So, and this is one of the reasons that tension is exactly the same everywhere, okay? Because think of like this, right? If there's a pulley and you have a rope going around the pulley like this, if the tensions are different, the pulley will not rotate. Sorry, if the tensions are the same, the pulley will not rotate. The tensions have to be different, right? Imagine, right? Pulling at both ends, in order for the pulley to rotate, one has to be stronger for that kind of to rotate. But here we don't care about that. We can say that pulley doesn't rotate at all. It just sits there and then just a rope goes around it. So, or we can just say it's a massless pulley and a frictionless bearing. So we can then completely ignore any information about the pulley, which is just there for the rope to go around it. But it doesn't really do anything. We have to wait until chapter 12 to actually consider rotating pulleys, where then, things are going to be a little bit different. So, but here, as soon as you see massless pulley, frictionless bearing, then we can just say, all right, so all it does is just allows the rope to go around like that and kind of change the direction, right? Kind of goes like that. But the tension is going to be exactly the same on both sides of the rope. Okay. So now the idea is, it says the rope and the pulley are among the interacting objects, but you'll have to decide if they are part of the system. Okay. Now our goal here is to do this, right? Draw an interaction diagram, and that's the one where we have to kind of recognize which forces are interacting with one another. Identify the system on your interaction diagram, your free body diagram from each object, and use a dashed line to connect the members of an action-reaction pair. Okay, so a lot of things happening over here. So remember, the idea is A is going to be accelerating, down because it's heavier. So there's going to be acceleration of A, which is going to be in the downward direction. B is going to be then accelerating up because, if A is going down, B will then be going up. So that means what we're going to do here is we're going to then try to find a way to represent all of this. So from the point of view of interaction diagrams and free body diagram and things like that. Okay. Now, for the interacting or interaction diagram, so generally what we want to do here is we want to look at in terms of what is my system. Okay, so what is my system, and what are the, let's say then, forces that are internal and what are the forces that are external. Okay, so here what I can do here is to understand that if I'm taking A and B, block A and block B, they're interacting and they kind of move together when you have all these forces acting. So my system will then include both of them. So what we can do here is something like this. So sort of like I make a rectangle like this and say, so this is going to be my system. Okay. So this is your system, and what you have here is then you identify the objects. So which of these objects are going to be part of your system? Okay, so you have technically a couple of things, right? So you have A, B, you have then, and you can see, right, it says a rope and a pulley are also among the interacting objects. So, but what we're going to do here is we're going to say that, A is accelerating, it has mass and it's accelerating. B is also has a mass and it's accelerating. But pulley and strings or rope are massless, so technically they are not accelerating, so we can kind of ignore them as object part of my system, because I can't have system where, remember, right, acceleration of all the objects in your system should be the same. That means I can have to say acceleration of A is same as acceleration of B, and that clearly those two blocks are accelerating. But then, as I said, right, if I'm looking at the acceleration of the, let's say, rope, I'm going to say then, let's say some kind of net external force acting on the rope, and I put mass of the rope, but we're told that, rope is massless. That means I can't find acceleration if rope is massless. Same thing with the pulley, right? If pulley has no mass, it has no acceleration. But I have to say that, the system has acceleration. A has acceleration, B has acceleration, but pulley and rope, they don't, so they can't be part of my system. So my system only has, block A and block B. Okay. All right, so that's basically two objects that, part of my system. So what you do here, you create a, you do like a rectangle where you put your objects that are interacting, and that's going to be then the system. All right, so then what you do here is you recognize all the agents that are acting. So for example, there's a, the surface, right? So it gives you, a friction and things like that. So for example, there's surface 1 and surface 2. So for example, one of them is an internal force, the other one is an external force. Okay. So what's the internal force here is the friction right here between those two. That will be the example of an internal force. So if it's an internal force, because it's the force that is only due to the fact that A and B are interacting with one another. All right, so then one of the things we can do here is I can then maybe like use something like this. So these two are connected by this. I'm going to put like F2, so friction 2, or friction. I'm going to use that as a friction 2, like or actually let me do. Like I guess I can just do I can do friction 2. Like let's put it like that. So friction 2, which is going to be from surface 2 is going to be internal force. Okay. All right, so there's also that's, there's also a tension in the rope, right? So that means I can look at it in terms of tension. So basically, they are also interacting like this, and there's this, a friction too surface. So it's, again, it's something that acting, but it's, it's external. And then became like a gravity, right, is acting. So something like this, right? So it's some external force acting on them. So those are then going to be the external forces. Again, like I said, I don't necessarily do or require you guys to use interacting diagrams. I'm not going to be asking you to do that in the exam or anything like that. So, but it's a good, useful tool that kind of, this particular textbook, uses. I haven't seen outside of this textbook, other textbook kind of use this diagram, just kind of interesting. All right, so, but what's more, let's say, something that I'm going to require you guys to do here is always to pay more attention to free body diagram. So for free body diagram, then let's say at this point, we don't do free body diagram for the entire system. So when you're doing free body diagram is you want to then separate your system into two parts. So on this point, we're going to be then looking at B separate from A, and then do the free body diagram for B, free body diagram for A, and then recognize and find all the interacting systems. Okay. All right, so let me get rid of this so we can have more space here. So let's look at then free body diagrams. So what I have here is we have an incline, so I'm going to tilt my coordinate system. So I'm going to say that here's this, a system for B, and I have A. So I'm going to do that here for B. Since B is going to be accelerating up, I'm going to take up as positive X. And I'm going to put B here at the origin. And I want to recognize and identify, recognize, and with correct direction, and put all the forces acting on only B. Okay. So one obvious one, right, is going to be gravity. So gravity is going to be acting like this. So F of G of B. Okay. Another very obvious one will be the tension, right? There's going to be tension. Okay. Which in this case, you can say, for example, is tension, A acting on B. Because, it's in a way, it's A that is pulling, right, by, from that rope. Well, B is sitting on top of A, so there is a surface here, which then gives us two forces, normal force and friction. So the normal force is going to be perpendicular, right? And then since B is going to be accelerating upward, there's going to be friction. So then, let me actually label it like this. So this is normal force that A exerts on B. And then here's a friction that A exerts on B again. And it is a kinetic friction because they're accelerating. All right, so these are going to be then, this is going to be free body diagram, all the forces acting on B. And it's going to accelerate upward with that acceleration. Okay, so let me know if you have questions. Let's look at then A. So for A, again, I have a tilted system. But A accelerating downwards, so I'm going to take down as my positive direction for X. And that's something you can do. You can have two of the systems have different, positive, negative directions. All right, so here's A. All right, so let's recognize all the forces acting on it. So we have, obviously, gravity, there's this one. This is the gravity of B of A. Then I have normal force coming from the surface one, right? So normal force from surface to A. Then another one here is that, there's a rope. There's a tension here. This is a tension, which we can write as B on A. So because it's connected to B, we can just say that. All right, so now what we can have here is we also have, we were told that all the surfaces have friction. So then surface one exerts friction on block A, which is something we have, we know how to do that, right? So it's to the right. There's going to be a friction. Let's put like as friction one, right? So the surface one. But what's new and not very obvious is that there's also another friction. And this friction is coming from the fact that there are B sitting on top of A, and there's a surface-surface interaction. So there's going to be also a force of friction from that particular surface. And remember, right? So all the frictions always opposite to the motion of the object. And now my object A is going down, so that friction from block B will be upward in opposite direction. Then the friction that B exerts on A. All right. But we're not done yet. There's one more thing, because the same surface 2 that gives us this friction, it also gives us a normal force, because, if you think of like B sitting on top of A, but you can also, if you kind of flip it, you can say, okay, A is sitting on top of B, right? So there's a surface there. There's also a surface normal force, and this is going to be then B on A. Because remember, if I'm looking at this, right, it's going to be this normal force in that direction. As you can see, right, there's 1, 2, 3, 4, 5, 6 forces acting on A. And it is accelerating downward with acceleration. Okay. All right. So those are the free body diagrams for block B and block A. And one of the things that this problem was asking us is to use a dashed line to connect the members of an action-reaction pair. All right, that means for every action, there is opposite or equal reaction. And that's the key, right? So opposite reaction, that means will be A and B interacting, because those are the two things in my system. When they are interacting, right, they exert force on one another. That have the same magnitude but opposite directions. And we can see that that's due to the fact that, for example, here's this normal force A on B is upward, and here's normal force B on A is then downward. And those are example of action-reaction interacting forces. These are this first pair that we found. We also have the friction that they exert on one another. We can write FAB is down, FBA is up. They're again in opposite directions. So that's another action-reaction forces. Okay. There's also tension. Tension AB and BA are basically, interacting as well. Okay. So in one case, it's, in the direction of acceleration, another case in the opposite direction of acceleration. So that's, I think this one is that. That's also interacting ones. Okay. So that should be pretty much all of them. Those three things are kind of interacting. All right. Any questions? All right. Let's then look at something else. Here we have, again, two blocks. Block B rests on the surface for which the static and kinetic coefficients are 0.6 and 0.4 respectively. The ropes are massless. which is a good thing. That means all the tensions are exactly the same. What is the maximum mass of block A for which the system is in equilibrium? Okay, so think like this, right? So what we have here is that B here is at rest, and there is a friction there that keeps the whole system at rest. Because A here is basically, being pulled by the gravity, and it has no normal force to balance it, but it is balanced by the tension here. But if, let's like weight of A. If A has too much mass, then the gravity will be stronger than the tension that can keep. And this tension here is the same as this tension here. So that tension here is equal to the friction force right there. So all of them are kind of like equal to one another. They're all in equilibrium. But if this is basically at the maximum, let's say capacity, that means everything here is barely holding on. So any increase in mass of A will then make the system accelerate. And that's what we want to find out, right? What will be the maximum mass for A for which the system still will be in equilibrium? Okay. All right, so what we do here is we then look at individual A and B and try to find what will be then the mass of A, because for our goal here is to understand that all the forces acting on A, all the forces acting on B, they all have to cancel each other for the system to be in equilibrium. All right, so let's start then with A. So A has only two forces. It has tension upward. I'm going to use W for weight, so weight of A downward. Okay, so which means that I have then equation 1 will be weight of A minus tension equals 0. The system is in equilibrium. And then I look at B, and I can say that B has 4 forces acting on it. So there's a tension to the right. There's a friction, static friction to the left. There's normal force up, and there's a weight of B down. Right. So that means, in a way, what we can do here is we can then see that I have equation 2, which is going to be the horizontal forces for B. That will be then tension minus static friction equals 0. They cancel each other. Same way, then I have equation 3, which is then vertical forces acting on B. And that will be then normal force minus WA equals 0. Oh, sorry, WB. Okay. So this will be then our equation, right? So we have 3 equations. And remember, our goal here is to find the maximum mass of block A. So from here, these 3 equations, we can kind of modify. We can say, okay, so equation 1, it tells us that the weight of A is equal to the tension. Equation 2 tells us that tension is equal to the static friction force. That means this is equal to the static friction force. But we know that static friction force is the coefficient of static friction force times normal force. And then equation 3 tells us that normal force is equal to the weight of A. That means this is equal to the coefficient of static friction times the weight of A. So that means our equation ends up being this: weight of A is equal to the coefficient of static friction times weight of, weight of B. I keep doing this A. So weight of B. Okay. Now, weight of A is mass of A times G on the left side. On the right side, then coefficient of static friction times weight of B, which is mass of B times G. Then here I can see that I can cancel G from both sides, and then solve for mass of A. It will be then coefficient of static friction times mass of B. The coefficient we were given as 0.6. Mass of B here is given as 20 kilograms. Then we can just solve for that. So mass of A has to be 0.6 of 20, which is 12 kilograms. It cannot exceed 12 kilogram. Otherwise, the system will not be in equilibrium. And that's how we would solve this problem. All right, any questions? All right. All right, guys, so let's do this, right? So let's take a 10-minute break. So it's 7:10, so we're gonna resume at 7:20 p.m. Right, so we'll resume the lecture at 7:20 p.m. All right, guys, so let's go ahead and continue. All right, so here's another example. So, so for this one over here, again, okay, right, so we have two objects. So we have A and B connected to one another. And at this point, again, you have one rope connecting them. So this time we have one of them going to the right, the other one going down. So it's like, again, two different directions. But again, everything else is pretty much the same. So you have a couple of ways of looking at this type of problems. All right, so let's read the question. So you have two boxes that are connected by a cord running over a pulley. Again, for us, cord, rope, string, that all basically gives us, this tension force. So we're given that coefficient of kinetic friction between box A and table is 0.2. That means this surface here is a rough surface with a coefficient of kinetic friction of 0.2. We ignore the mass of the cord, which is good because that means tension is the same everywhere. And any friction in the pulley, which means we can assume that force applied to one end of the cord will have the same magnitude as the other end. Now, what it means here is, if I look at this tension that acting on A, which is going to be to the right, and then the tension acting on B, which is going to be up, are going to be exactly the same magnitude. Obviously, they have different directions, horizontal and vertical and things like that, but they will have the same strength. All right, so we wish to find then the acceleration A of the system, which will be the same, again, right? Same for both boxes, assuming that cord doesn't stretch. And because it is, right, if you have two things that are connected to one another, and they are accelerating, they will always have exactly the same acceleration. Even if I had, like, let's say another box right here, box C that was connected and moving on the same surface, right? This will also have exactly the same acceleration. All three of them will have exactly the same acceleration because they're all connected and it's an interacting system. All right, so we want to find acceleration. That's one of the things we want to know. That means acceleration of A going to be the same as acceleration of B, which we're going to try to find, but we can just say that this is the same as system acceleration A, and that's what we want to find. Right. Now I'm going to add one more thing here. Let's say we also, let's just part A. We also want to find then tension. What is the tension? Again, so tension of acting on A is going to be the same as tension acting on B. There's going to be some tension T. But again, let's say what would be the volume or what would be the expression for that tension? All right, so again, this is our problem, right? Two blocks, and we are given. So let's say in this case, we can think of, like, let's say we're given mass of one, or sorry, mass of A, which is 5 kilograms. And we're given mass of B, which is 2 kilograms. Okay, so those are the things that are directly given to us. And obviously we're given coefficient of kinetic friction, which is going to be then 0.2. Those are the things that are given. So what we do here is then we treat this as a system of A and B interacting. And what I would do here is I would then take A to be, let's say, system A, and B, which is like here, B, the system B. And there has to be something that connects those two systems. And you can see, right, they are connected by two things. One, they have the same acceleration. Two, they have the same tension, right? Same rope, or in this case, a cord, right? Connecting A and B. So there has to be something that your, let's say, subsystems, connect to one another. In this case, those are the things that are going to connect them. All right, so let's start by looking at A. So we look at box A, and I'm going to then do a free body diagram for A. I'm going to take A to be some kind of a point particle at the center of my coordinate system. Then I do the forced free body diagram, right? So remember, right, every time there's a force problem, I expect you guys to do the free body diagram. That would be for the group works, that would be for the, exams and things like that. So, all right, so there's obviously a rope, a cord to the right, so there's a tension A. There's a earth exerting gravitational force, so let's put this F of G of A, or can put like WA for the weight. And obviously normal force acting up, and then friction, kinetic friction to the right. So if I have to then use force table, I have to then do that for the four forces that I identified. So there will be the tension A, there will be kinetic friction, then normal force, and Fg of A. All right, so I can see that tension acting to the right, so it's positive horizontal force. It has no y component. Friction to the left, so horizontal force negative, no y component. Normal force straight up, so no horizontal plus y in a y direction. And then gravity pulls it down, so it's going to be negative MAG. Since A going to be accelerating along the surface of the table, there will be no acceleration in a y direction, but we will have acceleration in the next direction. So this will be then the free body diagram and a force table for A. So let me know if you guys have any questions on this. That means I'm going to get two equations, which is going to be TA minus F of K equals M1A. So MA times A, mass of A times acceleration. Then I'm going to get equation 2, which is normal force minus MAG equals 0, which then tells us that normal force is equal to the weight of the object A. So it's equals to MAG. And in a way, we can calculate this because we know that it's 5 kilograms. So 5 times 9.8, it's 49 newtons. So the normal force is 49 newtons. All right, so then what we have here is equation 1. There's not much I can do with that because I have two unknowns. I don't know the tension in A, and I don't have the acceleration. So those two things are unknown to me. So I'm gonna keep that like that for now. And then go to the system B and see what I can do with that. Well, system B is pretty much, we're just looking at this, right? So box B. Okay. So for that, we're gonna then say, all right, so here's my free body diagram. And the idea is it's just object going down. It's not a free fall, but object accelerates down. So I'm going to take them down positive. That's going to be my positive direction for B. And this is there's a really good reason for me to do that because acceleration of B is down. So if I take down as my positive, then I can take mass times acceleration part of the equation to be positive because it's going to be in the same direction as what I identified to be positive. All right, so two forces that I have acting on B, again, this is B, is going to be then gravitational force acting on B, and then tension acting on B. So if I then do the force table, here's then the FGB, and this is then TB. 0, 0, 0, nothing in a horizontal direction for the B. But in this case, what I have here is, since I'm taking down as negative, then this MBG will be positive, but then tension B will be negative. I'm doing this because then I can do this M mass of B times A as positive. If I take up as positive, then it would have been, this is negative, this is positive, but then I had to manually put negative here because acceleration is negative. So it's just something for convenience, right? We just take down as positive if I know that it accelerates down. So this is positive, this is negative, but this becomes positive. All right, so remember, I already had equation 1, and that was tension A minus kinetic friction equals mass of A times acceleration of A. I had equation 2 that was normal force is equals to then mass of A times G, that was 49 newtons. Now I get another equation, which is right from here. And that will be MBG minus tension B equals NB times AB. So I get those 3 equations. All right, let me know if you guys have any question on any of this. All right, remember our goal was to find expression for acceleration or calculate acceleration. And I have now 2 equations, 2 unknowns. Tension is unknown, acceleration is unknown, but what I know here is this. This is things that are basically something that we can assume from given information, that tension of A is equal to tension of B. That means I can come back and I can get rid of the subscript A and B from the equations A1 and 3. This can go away, this can go away, because I can say that tension is just T. Same way I know that acceleration of A is same as acceleration of B, I can just have acceleration of the system. That means I can get rid of the subscript as well. And then what I can do then, I can actually add these 2 equations together, 1 and 3. If I add equation 1 to equation 3, then if I'm adding those together, the tension is positive in equation 1, is negative in equation 3. And if I'm adding on the left side, I'm just going to have those cancel out. And I'm going to have then MBG minus F of K equals MA times A plus MB times A. I end up with that as a result. So from here, I can switch the sides. I can say it's MA times A plus MB times A equals MBG minus F of K. Then I can factor out A, acceleration, becomes MA plus MG, so MA plus MB. And on the right side is MBG minus F of K. And then finally divide both sides by MA plus MB. So then acceleration will be MBG minus F of K divided by then MA plus MB. So then this will be my final expression for acceleration, because at this point, I have pretty much everything that I need to solve it. All right, so then let's plug in values. Let me say, I already forgot the mass values. So it's 5 and 2. And 0.2 is that, okay. That means it's 2 kilograms times 9.8 meter per second square. Then minus F of K. Well, F of K is, remember, it's mu K times normal force. Well, it's mu K. Well, we already have normal force, so I can just say basically it's 0.2 times 49 newtons, which is the normal force we calculated. Then this will be then 5 kilograms plus 2 kilograms. All right. So at the top, 0.2 times 9.8, then minus 0.2 times 49. Here I get 9.8 newtons. At the bottom, I get 7 kilograms. And I have then 1.4 meter per second square acceleration. So then acceleration of both of those objects will be 1.4. Both will have a acceleration of 1.4. It will be then the box A will have then 1.4 meter per second square I hat. And then B will have 1.4 meter per second square J hat. And it's going to be positive because I took the down as my positive direction. Okay. All right, guys, let me know if you have questions. Now, for example, the next part, what I can do here is, remember I added a secondary part. I asked you also to give me tension. So let's say what I have here is once you get to this part and have an expression of acceleration, you can see, right? In this expression for acceleration, we eliminated tension basically. When we added 1 and 3 together, I eliminated tension and I have an expression that is independent of tension. All I needed for this is the mass, basically the mass and well, mass of A, mass of B, and I needed the mass to find the kinetic friction and the normal force, right? So giving MA and MB, I could calculate acceleration. But now that I calculate acceleration as well, I can go back and calculate the tension. And to calculate the tension, well, I do have that equation 1 and equation 3. Again, that means go back to those equations and then solve for the tension. So for example, if I go back to this equation 1 in the original format, then I can say that, all right, so equation 1 was tension minus F of k equals mass A of times acceleration. And that means tension is equals to mass of A times acceleration plus kinetic friction. Well, that was 5 kilograms for the mass times, acceleration of 1.4 meter per second square, then plus kinetic friction. And kinetic friction was 0.2 times 49 newtons. And let's see what we get for that. That's 9.8. 9.8 newtons. That means this plus 5 times 1.4. So 16.8. That means I get 16.8 newtons for the tension. I could also use equation 3 to solve for tension, but it doesn't matter. You find acceleration, then you find tension. Okay. Now, the idea for the problem like this is you have usually 4 variables. Those 4 are going to be mass of your box 1, mass of your box 2. They could be 1 and 2. There could be A and B, whatever, right? So basically, you're going to have 2 blocks, for example, or boxes. Then you're going to have maybe like 1 rope connecting them, and they're going to accelerate. So the idea is you think like, right? So you have 4 variables. Mass of A in this, let's use A and B. So mass of B, then you're going to have a tension, then you're going to have acceleration. So the idea is that tension of A is going to be tension of B, so we can just call it just tension. Acceleration of A is going to be acceleration of B, so we can just call it acceleration. Okay. But more or less, you have 1, 2, 3, 4 variables. And what you can see here is I gave you mass of A and mass of B, and using those, you solve tension and acceleration. So if I give you two out of those 4, you can calculate the other 2. Now, what I can do here is I can change it a little bit around, right? Maybe I can give you tension and mass of A, which then should be enough for you to calculate mass of B and acceleration. If I give you acceleration and tension, you can use them to calculate mass of A and mass of B. That means any two that I give you, you can calculate the other two by going through the same similar steps that I just had. That means break down them into two systems, use, you get those equations and then rearrange them and find that. But the idea is that any of these four, any two of these four variables that I give you, you should be able to find the other two. Doesn't matter which combination. Okay, so, and not much I can do with this, right? So I can have the surface frictionless, I can have the friction like we did in this example. Obviously, it's easier if it's no friction, but even if it's friction, you can see, right, it doesn't necessarily make it more complicated. All right, so any questions? Okay. I have another example that is pretty standard example that we always do, using two blocks. So in this particular example, you can see, right? So you have, again, two blocks connected by a rope, and the rope goes over the pulley. It's just both of them are vertical, let's say they can move vertically. There is no surface. So this is usually known as the Atwood machine. So Atwood machine. And generally what you have here is, you can think of like, right? So if you have two blocks like this connected, you're always going to have like two blocks, right? So let's take this to be M1, take this to be M2. If M1 is equals to M2, then your system will be in equilibrium. It's not going to move. You're going to basically have your system being at rest. But as soon as you have one of them much heavier than the other one, then the system accelerates. Again, we're going to assume that mass of the, what does it say? Well, let's call the string. Mass of the string is 0. Mass of the pulley is 0. And the friction of the pulley here is 0, right? Taking all of those things to be 0, then we can assume that we are pretty much looking at tension here and tension here to be exactly the same, and acceleration of the system exactly the same. But the idea here is, as soon as you have the mass 1 or mass 2 that are different, then your system can accelerate. So in this case, if I take this one, for example, to be mass 2, this one mass 1, like I have over here, you can see from the size of the blocks, right? There are different sizes, means that M2 is greater than M1. As soon as that's the case, M2 starts accelerate down, M1 starts accelerating up, and that's kind of what we have. So imagine, right? So you have this, you're holding the system in equilibrium at rest, 1 meter block M2 being 1 meter above the ground, and then you let go of the system. As soon as you let go, system starts accelerating. And then 100 kilogram, which is M2, going to start accelerating down. M1, which is unknown mass, going to start accelerating up. Both going to move 1 meter because that's the distance, to the ground. And what we're told here is that 100 kilogram block takes exactly 6 seconds to reach the floor when you release them from rest. And our goal here is to find the mass of that block 1. And again, taking the pulley to be massless, frictionless, the string to be massless, and assuming that they can have some acceleration and the tension in the rope going to be, the string going to be the same. Our goal here is then to find that. All right. So as I mentioned, the idea here is this, right? You have 4 variables: mass of 1, mass of 2, tension, and acceleration. And then I have to give you at least 2 out of those 4 for you to be able to solve the problem. I don't have to give you 3. I can give you only 2 for you to solve. And here, I give you mass of 2, which is 100 kilograms. I don't give you tension, but indirectly, I also give you acceleration. I'm telling you that indirectly because you're not told that, acceleration is this, but you're told that starting from rest, it's going to accelerate exactly 1 meter in 6 seconds. So basically, I'm going to, this problem kind of mixes it up a little bit. So it gives you a way to solve acceleration using kinematics. Because all you have here is this, right? So you have your object is right here at point A. And they're going to go down at point B. Displacement delta y, speed at A, which is initial velocity or is 0. And what we want to do here is taking the time to be 6 seconds, find, acceleration going from A to B. And that's something you should be able to, at this point, easily calculate, right? Give you initial velocity 0, I give you displacement, I give you time, solve for acceleration. That means before we can even go back and look at this problem from the dynamics point of view, we have to, let's say, use kinematics to solve for acceleration. Okay, so, and let's do that, right? So, again, given, so let's say initial velocity to be 0, because it starts from rest. The displacement here is to be 1 meters. Time to be 6 seconds. We want to find the acceleration of the system. Again, this is not a free fall. Acceleration is not equals to g. Sometimes I have students, in this problem, kind of wrongly assuming that it has to be equals to g. It's not a free fall. You have a tension there. But that information is already enough. Because what I have here is, I have equation where I give you initial velocity, displacement, time. There's no information about final speed, but you don't need that because kinematics equation 2 tells you that if you have the displacement, you can then use this as initial velocity times time plus 1/2 times acceleration times t squared. And you can solve for acceleration. Taking this to be 0, you can then rearrange and solve for acceleration. So rearrange this, then becomes 1/2 acceleration times t squared equals negative delta y. And then knowing that you're going down, which is delta y is -1, negative going to cancel out. So we can kind of ignore that part. So we can just say that negative, delta y is just, delta y, and it's just 1 meter long distance. And I just use this equation, rearrange and solve for acceleration. So it will be 2 times 1 meters divided by time, which is then, it's going to be t squared. So it's going to be then 6 seconds squared. Going to rearrange and solve that. All right, so this will be then 2 meters divided by 36 seconds squared. So 2 over 36. So we're going to get 0.05, I guess 0.6 maybe, meter per second squared. Okay, so this will be then, that's rather really long time, but okay. So 0.06, meter per second squared, that's for the acceleration. Right, so as you can see, right, so that means I go back to what I just said, right? So that means you have mass 1, mass 2, tension, and acceleration. And I need to give you 2 out of those 4 for you to solve. I didn't give you tension from the beginning, but I gave you a way to solve for acceleration. And here you have to understand, right? So sometimes if you're given certain information, you can use them to find acceleration. Here you use kinematics to find it. All right, any questions? All right, so now that I have acceleration, then I can go back and look at this from the, again, kinematics point of, dynamics point of view. Okay, I can say, all right, so what I have here is, I have the pulley. I have M1. And I have M2. and I have a rope that kind of connects them like this. So what I would do here is I'm gonna then split this into two systems like this. So this is gonna be one, this is gonna be two. For the first one, I know that M1 gonna accelerate up. So I'm gonna take up as my positive direction. I can even ignore horizontal axis altogether because nothing horizontally going on. So I can say if this is my M1, I have two forces acting on it. There's gonna be one, which is gonna be tension upward, and then gravity, right? FG1. I guess it's simple enough that we don't necessarily need to have like a force table. So I get equation 1 from here, which is going to be the tension. Let's say tension 1 minus F of G1 equals mass 1 times acceleration. Remember, F of G1 is just nothing but M1G. So tension 1 minus M1G equals M1A. Then I look at, so this is, again, this is 1. Then I look at the second one. Well, for the second one, because it's heavy, it's going to accelerate down. So I'm going to take down as my positive direction. So then here's second block. And what I have here is the weight of the second one is now stronger than FG2, and then tension up. So what I get here, equation 2 will be M2G minus tension 2 equals M2A. All right. Remembering that tension 1 and tension 2 are the same because it's the same rope. We go back and get rid of the subscripts. And then what I want to do here is, remember, our goal was to find M1. What is M1? But now at this point, I already have the acceleration, which we just calculated. So I still don't know the tension, but again, I don't really need that because I can add those two equations and eliminate tension. If I add them to this tension over there, goes away with this one. And I end up with M2G minus M1G on the left side, and M1A plus M2A on the right side. Well, I want M1A, I want M1. So I rearrange such that all M1s on one side, anything that doesn't have M1 as another side. So if I rearrange, it will be then M1A plus M1G equals M2G minus M2A. Then factor out M1. So A plus G equals, and then here I can factor out M2, G minus A. And then cancel, sorry, not cancel, like, move the other one, MA to A plus G to the other side. So M1 is equals to M2 G minus A over A plus G. And then finally, so forth, M1. So M2 was 100 kilograms. So, but what I have here is this, right? G minus A over A plus G times M2. So M1 is equals to, so 9.8 minus 0.05, I think 0.06 over 0.06 plus 9.8 for acceleration, then times 100 kilograms. Okay. So this is the calculations, assuming I calculated A correctly in the first place. So 9.8 minus 0.06 divided by 0.06 plus 9.8. I get 0.987 times 100. I get roughly 98.8 kilograms. That's why their difference is very small. So that's why it took us 6 seconds for it to just go down 1 meters, which is quite a long time. So this was the steps. Let me know if you guys have questions. All right, so let's do this. Let's take another break. So it's 7:57. All right, so I'll give you, I guess, like 12-minute break. So I'll be back at 8:10. So we'll resume at 8:10, guys. So take what 11, 12-minute break. All right, guys, so let's go ahead and continue. All right, so here's then another example. So for this one, we have now making it a little more interesting. So we have now, again, two boxes connected by a rope. There's a pulley, but now, one is on an incline instead of like a flat surface. So we're given is on an incline, 10 kilograms, and it rests on a surface. There is a 37-degree incline relative to the horizontal, relative to the ground, let's say here. And it's connected by a lightweight cord, which is another thing, right? So it says lightweight, that means we can ignore the mass of the cord, which passes over a massless and frictionless pulley, which is, some of those things that we want to look for. So mass of the pulley 0, mass of the cord 0, and then friction of the pulley 0. So we can ignore any effect from cords and pulleys. And then we're told that it's connected basically to second box B, which hangs freely as shown. That means at this point, we're looking for, or looking at system in equilibrium. Now, part A says if the coefficient of static friction is 0.4, and obviously it has to be for this incline, right? Determine what range values for mass B will keep the system at rest. Okay. All right, so let's look at let's look for that first part in terms of system still being in equilibrium, and then we want to know in terms of what should be the value of B, mass of B to be, so that we are in equilibrium and the system or the friction here is able to keep it out. Okay, so again, what we have to do here is we have to break it down into two subsystems. So here is going to be then B, and this one will be then A. We have those two systems. So let's start with the easiest one, right? So the system B is the easier one. It has then the weight of B down and then the tension up. So which means that since the system is in equilibrium, it doesn't matter, right? Which one is positive, which one is negative. So for system B, what we get here is that the tension equals to the weight of B, equals then MBG. So let's call this equation 1. So the tension and weight of B are equal to one another. All right, so then let's go to then system A, which is a little bit more complicated because it has friction as well, and there's an incline. So I'm gonna tilt my coordinate system, and again, it's in equilibrium, so it doesn't matter if I take up or down positive, but let's just take up positive for now. And what we have here is, let's say, I guess, doesn't matter. So here's then A as a point particle, and I have a normal force acting in this direction. So this is Y, this is X. So this normal force. I have gravity, right? So weight of A acting such that it has 37 degree here. And now I have two forces. One is the tension in the direction of the cord and also friction. Okay. Now, the direction of the friction will be, in a way, dependent on which of these two volleys, right? So like, let's say mass of A or mass of B. So the idea is that which of them is heavier. So for example, if B is heavier than A, but let's say overall, right? In this case, if this weight of B is heavier than tension, then the system will try to move overall to the left. That means mass of B will go down, would want to go down, and A will want to go up the slope. In that case, friction will be downward direction. If A is much heavier than B, let's say, then B would like to slide down. In that case, then the friction will be in the opposite direction. So basically, you have those two different scenarios, right? So if those two different scenarios in terms of in which direction will be the friction force. So that's why this particular part A is asking for finding the range of values for B, because it depends if the B is heavier than A or A is heavier than B. All right, so which means that we can have two different directions for the friction. Okay, so that's basically will give us those two different values for B. So let's look at in terms of if A is much heavier. So if A is much heavier, then as I said, right? So that overall the system will try to move in that direction. So then the friction will try to prevent that. Then the friction will be acting upward like this. Again, we're still in equilibrium, but still the static friction will be, in an upward direction. Okay. So let's do a force table for this one because there are a lot of things happening here. All right, so let's start with, let's say weight of A. So then we have normal force, then we have static friction, and then we have tension. Net force. Again, we are assuming we're still in equilibrium. All right, so if this is the scenario, that means, mass of A is, heavier than B. In that case, let's say, again, taking, for example, up as positive, we have then, this makes it quadrant 1, quadrant 2, quadrant 3, quadrant 4, kind of reverses things a little bit for us. So that means here I will have mass of A times G, which is the weight magnitude, sine of theta for the X component, and mass of A times G, cosine of theta for the Y component for the weight of A. Because that happened to be my quadrant 3, both will be then negative. Normal force has no X component acting in a positive Y direction. In this case, static friction will be my positive direction because, again, I just chose up to be positive. Has no Y component, and tension will be positive and has no Y component. Okay, that means from system A, then I'm going to get two equations. Let's call this equation 2. That will be then tension plus static friction minus MAG sine of theta equals 0. And then equation 3 will be normal force minus MAG cosine theta equals 0. So those are the three different, equations that I'm going to get. Generally, when you have something that is just moving vertically only, you have just one equation from that. But something that is, either moving on a flat surface or an incline, you're going to get two equations from that. All right, so remember, our goal here is to find mass of B, right? So it helps that the system is in equilibrium, and it helps that in a way the tension is equals to then weight of B. So that means if I go back to equation 2, I can replace that. So I can modify equation 2. Let's do it here. So equation 2, then the tension can be replaced with weight of B. So it's MBG, then plus static friction. We'll change that later, right? So plus static friction minus MAG sine of theta equals 0. then I can solve for mass of B, right? So mass of B, G equals then, move the other two to the right. So it's going to be then MAG sine of theta minus static friction. Then I can finally go back to equation 3 and show that normal force is equals to then MAG cosine theta. And since the static friction equals coefficient of static friction times normal force, static friction equals then coefficient of static frictions times MAG cosine theta. That means MVG equals MAG sine of theta minus mu s MAG cosine theta. And then from here, we can just cancel G from both sides, which means then mass of B is equals to MA sine of theta minus mu s MA cosine theta. I can even factor out MA and just have sine theta minus mu s cosine theta. And that will be then the expression for that. All right, so I can calculate the value. So M of A was given as 10 kilograms, and then coefficient is 0.4. So 10 kilograms times then sine of 37 minus 0.4 times cosine of 37. So let's calculate that. I got 2.82 kilograms. All right, so let me know if you have questions, but this will be then, again, you can see, right? We considered mass of B to be much lower than mass of A, because if that's the case, then A would try to slide down an incline, so the friction will be upward. And we end up with calculating exactly that. All right, any questions? All right, so the other scenario would have been then, if I come back over here, I can then take this, right? So the mass of B is greater than mass of A. Because under this condition, you can still also have an equilibrium. If that's the case, then equation 1 would still be the same. If, again, you're still in equilibrium, it's heavier, but you're still in equilibrium. So tension equals the weight of B. The difference would be in system A, friction then will be in the opposite direction. So the friction now, again, because now B is heavier, it will try to go down and it's going to try to pull A upward. And friction, we're going to try to prevent that. So friction will be in this direction. It's going to try to help the weight of A to keep the system in equilibrium. That means what will change for this particular case is the direction of the friction force. It will be then negative. Okay. So everything else is the same. You just now, again, this is here negative. So if we come back here, change everything around. So this will be negative. So if you move it to the other side, it will be positive, positive, and positive, like this. So if then we have that, all we have to change here is just add those two terms together inside the parentheses. So 10 times sine of 37 plus 0.4 times cosine of 37. And I'm going to get 9.2 kilograms. Maybe not necessarily like mass of B is greater, but assuming I did correctly, right? But basically it will be something like this. That means mass of B can be greater or equals 2.8 kilograms. or less than or equals to 9.2 kilograms. For all of this range of values, your system can maintain the equilibrium. If mass of B is lighter than 2.8, then A is significantly larger, so the system going to accelerate down. If MB is greater than 9.2, then it will be this significantly heavier weight than the tension. So the system overall will go then to the left. So that's kind of what we have. That means this is the range of values for mass of B, for the system to be in equilibrium. All right, so I think let me know if you guys have questions on this. But I think part B says then, if we then take mass of B to be 10 kilograms, which you can see, right? It exceeds the maximum range right here on this side. So if mass of B is equal to 10 kilograms, that means that's it. The system is no longer in equilibrium and B will start falling down. A will then start sliding up the slope. And if that's the case, that means we no longer have static friction. Now we're dealing with kinetic friction. So we have then mu K, and it's 0.3, which is always less than mu S. We want to know then what is the acceleration of the system. All right, so that means our goal will be to kind of come back to all of this and rearrange everything, but this is no longer, this is going to be, no longer equilibrium. So we have to kind of take this and change it up a little bit. Okay, so let's do that here. So if I go to system B, where I had mass of B before, what I'm going to change it is that now I have the weight of B exceeds the strength of tension. So from here, I'm going to get then MBG minus tension equals MB times A. That's going to be my equation 1. So it's going to accelerate downwards. I'm going to take down as my positive direction. Okay. And then for the system A, again, since assuming that all the entire thing going to accelerate up, I'm going to take up as positive X. So what I will have here is weight of A, 37-degree relative here, normal force. I'm going to get the tension here. I'm going to get the friction opposite of the direction of the motion, and it's kinetic friction, because now it's going to accelerate upward. All right, so I have, let's put this tension here, kinetic friction, weight of A, and normal force. All right, so the tension is positive X direction, no Y component. Kinetic friction is a negative X component, like negative X direction, no Y component. Again, this, like I said, right, this becomes 1, 2, quadrant 3, quadrant 4, because it's going up. So weight is in a third quadrant, so both components are negative. So negative MAG sine of theta, negative MAG cosine theta, and normal force 0 plus N. The only difference here, now I have mass A times acceleration for X component. Okay. Again, so let me actually move this one here. This was equation 1. Then equation 2 will be form system A. So tension minus F of K minus MAG sine of theta equals MA times acceleration. And equation 3, normal force equals mg cos theta, MA mg cos theta. All right, so I have these 3 equations. All right, so what I will do here is, let's actually move this equation 3 here from here. We don't really need that. We only need that to get the kinetic friction value. So it's mu k times normal force, so mu k times ma g cosine theta. That's just find the expression for kinetic friction. Then what we have to do here is, since we want acceleration, we don't care about tension, we can add these two equations together and eliminate tension. It will be then mbg minus fk, which is going to be then mu k mag cosine theta minus mag sine theta. And this is then going to be equals on the right side, then I have those two added together. So ma plus mb times a. And you can see, right, all I have to do is just divide by both sides by that sum of the mass. So acceleration equals mbg minus mu k mag sine theta minus mag, or sorry, this cosine theta. Mag sine theta, and then ma plus mb. Okay, so then this will be then the expression. So the only thing I can factor out at the top is just acceleration of gravity g. So a is equals to, so mb minus mu k ma cosine theta minus ma sine theta over, so they both 10 kilograms, so 20 kilograms times g. So we can look at it in terms of fraction of a g. All right, so we can calculate here. So 10 plus 0.3 times 10 times cosine 37. Minus 10 times sine 37. By 20. All right, so I got 0.08 g, which means I got 0.77 meter per second squared. All right, so that will be then acceleration of the system. All right, guys, so any questions? Okay, then, so that's pretty much it. I'm done with this chapter. We did a lot of examples, so hopefully this will help you with the homework assignments. Don't forget, so tomorrow you have to go to campus to do in-person labs, and then I will let you know about Wednesday, and I'll have then the submission for the Thursday's lab due tomorrow. So I'll have that submission open for you guys, so you guys can submit. And I'll have then, since July 4th is a holiday, I'll have then tomorrow's lab due Friday instead. So Friday midnight. So I'll give you like an extra day to work on that. All right, so let me know if you guys have any questions. Otherwise, we're done for today. This is being recorded, so I will post the recording for this one. And I will upload it on Canvas maybe later today or tomorrow morning. Okay, it takes a while for it to upload to Canvas, to Cloud. So then as soon as I get that, I will upload it. All right, guys, so then have a good rest of the day. I'll see you all Wednesday. Take care.